The topic of the workshop is modeling the velocity of a pullback toy. Is it right?
That's right. Yep.
Yeah, perfect. I think it's time. So 11:15.
Okay.
Okay.
Well, thank you, Buna. And
Sure.
thanks to those of you who decided to come play with toys for the hour. It's too
Sure.
bad that we couldn't ship out a toy to every participant to actually have one handy. The sort of the star of the story for me today is this little truck that you see also on our slides. That is a little strobe light photo that I made a long time ago with that toy truck that comes out of a cereal box. And that shows you the quality of equipment that you really need to have to do this modeling scenario. And that's what we're going to be talking about today. And I think before we even go any further, I want to thank Brian Winkle for introducing me to Tova. She and I did not know each other prior to, I guess, maybe December, technically by email, and January by talking to each other. And I had worked on a modeling scenario that is about the pullback toy, but I haven't taught differential equations since I worked on it. And Tova actually used it in 2 calculus classes last semester, which is great. So combining, everything that we've done, we can kind of go full circle on the project, which I wouldn't have been able to do otherwise. So we're going to skip the abstract, and I think, Tova, do you want to say something about your involvement with Semiote, and then I'll...
Sure. Hello, everyone. I taught differential equations for the first time last spring, and in the process of reading about things, I guess, ran across Semiote as an organization that exists, and then found out about the practitioners workshop, which is an excellent introduction to using modeling in differential equations. That was not, I had nothing of that in my background, but this workshop in June was virtual for a week, and we learned so much, and it was a great introduction getting connected to the Semiote community and learning about practical tools and ready to go scenarios that you can use in your courses. So I'm new to Semiote, but very much enjoying it.
And strangely, even though I've been teaching differential equations since about 2003 or something like that, I did not know about Semiote until last spring either. And for me, it was interesting that the email that I got was forwarded by the dean of our College of Engineering to the chair of math from a faculty member in engineering who said something like, "Do you think we should let the people in math know about this?" And it was an advertisement for the DMARC and Mindy workshops last summer. And so the chair was like, well, who do I let know about this? He sent it to the people who teach differential equations, and a colleague and I both applied and participated last summer. And this is one of the projects that I worked on during the workshop, and was really fun for me just because I like toys. And if I can use them when I'm teaching, then that's so much the better. But it really amazes me. This is really a math organization, in my opinion, but it does tie into engineering and a lot of the sciences. And I was kind of embarrassed that I only learned about it through engineering faculty members at my school, and I didn't know about it any other way, but really glad to know about Semiote. And I think at this point, Tova and I really wanted to try to, this is supposed to be a workshop. And so we want to get people engaged. And one of the things that we wanted to know about was whether people have used modeling scenarios before, have written modeling scenarios, or if they're new to the whole thing. And so if you could use the chat or even unmute and speak, we would welcome that. And we'd love to know kind of where people are at on the spectrum, from like newbie to, I don't know, what intermediate, I guess, and advanced on that. Let's call advanced if you've actually written a modeling scenario, intermediate if you've used them, and everybody else we'll call a newbie. So I see the chat window. I don't see anything chatted in it, but I would love to get a little feedback from you guys. Okay, thank you, Cecil. And really, we don't mind if people unmute and speak. Thank you, Enrique. Oh, hey, Hector. So Nicole, you used this actual project? Cool. So I feel like we've got
Okay.
people who have used, have used other projects, and maybe nobody's written one in here. Oh no, Enrique has written some.
So Enrique is heavily involved in the work of the
With Deborah, right?
yesterday, Deb
Yeah.
Hughes Hallett.
Yeah, I remember
Yeah.
that. That's cool.
Yep.
All
Enrique's
right,
got
and
tons of experience.
spreadsheets, that's very cool. I think ours, we're intending to use spreadsheets as well, just because it's very accessible. And online, I did put in some MATLAB stuff too, but Excels are a really good common denominator. So, all right, well, with that, this is the overview for the workshop. We're going to try to spend only about 9 more minutes, according to my clock, Tova, on the creation process of this particular modeling scenario. Then we want to spend about 20 to 25 minutes with a little bit of modeling. Admittedly, it's just like a small piece of what students would get to do, but without being able to do a pullback toy share through Zoom, it's harder to do too much more than that. And then Tova's going to talk at the end about how her implementation of this project went with Calc students. So, but in the big picture, I think Tova and I are both thinking that it's not so much about this project, but about the idea that things you're doing in your class could be excellent modeling scenarios as well. And that would be great if you thought about creating some and making them available to others. So that's kind of the goal. So this comes from the Semiote website. It took me a while to find this exact verbiage. It's hidden, but I did find it. I put a link to it so that you can see it as well. And I kind of presume that Brian wrote this, but I'm not sure. That a modeling scenario is a pedagogical tool in which a modeling situation rich in detail motivates the study of differential equations. And so I have the ability to write on my slides here. And so we put down a few things that we think are important about modeling scenarios and what might make them more effective for classroom use, but we're open to input from you guys as well. And you know, there's a full range of things available on Semiote. Some of them can be done as part of a class, not even in full class, just to illustrate an idea. Others, some of the ones that I've done in my own courses are more like you get a group of students that are working on something for a couple of weeks and they submit a report at the end of a class. Maybe you need to wait far enough into a course for them to even have the knowledge to do the project in that case. But some things that we thought make modeling scenarios easier to use is when they blend in with the instruction of the course content, so that there's some point in the course where you can actually do this in a semi-natural way. That if they allow the collection or use of real data, those would be good things, because it helps make students buy into the usefulness of differential equations. And that it might be more compelling when there's actually some question that they're going to answer. Not just like, well, what's the local gravity in St. Louis, Missouri? Is it really 9.81 meters per second squared? Let's find out. But maybe something where they don't understand fully how something works, some process or system of equations. And by working on the project, they're going to be able to learn something extra about it besides just some parameter value or something like that. I don't know, Tova, did I miss anything that you think is important here, or anyone in the audience have other things that they would look for if they were trying to select a modeling scenario to use in a course? And I'm watching chat too, so if you want to put anything in the chat, that's cool. We're open to suggestions. Okay. So going back to the idea of like, where did this come from? Student participation in the coding, that's good.
That's going to be a theme of my results, Hector.
Yeah, that will come up later on, and so that's good. So when you apply to be in these workshops that Tova and I did over the summer, you have to submit a little bit of a synopsis of what you've done in differential equations or what you hope to do, and some project ideas. And one of the projects that I talked about in my application was this, it's a Boy Scout, like, what do they call these, Pinewood Derby cars? I was never a Boy Scout, but I like cars. And this one has been hollowed out in the back to accept carbon dioxide cartridges. And you can purchase, I bought one of these for myself, a device that actually has a little needle in it that you can control with a battery, and you can shoot off the car anytime you want. And so I did a project in 2010 on this CO2 powered car, and the goal was just to figure out how fast it could go. And so I was coming into the workshop last summer thinking that I was going to work on this and make a modeling scenario about that. But it has some drawbacks. First of all, you have to have this equipment, and you have to have the space and permission to do an experiment like this in your school, in your classroom space. I think when I did it, I was teaching in the summer, and I didn't think anything of it in my first couple of years teaching, that I'm shooting off this carbon dioxide car in the basement of the math building. I think I'd be afraid to do that now, that somebody would call me up later and tell me I need to find another job or something. But I did it then, and it was cool. And back then, cell phones were not as good, but that's how we made video of things. And the other thing that is maybe a negative to this idea is that the discharge of the gas from that CO2 cartridge is pretty hard to model. So we just kind of winged it back then. But if I was going to write a modeling scenario for Semiote, I would want it to be a little more precise. And that was an obstacle for me. So what I decided to do was make it a lot simpler. And I had this pullback car that I gotten out of a box of cereal at some point. And I thought, well, this has a lot of the same principles going on, like friction on the wheels, and it has a force that makes it move that we can try to understand. So on the left is my pullback car. On the right are the pullback cars that Tova sourced for her students when she did this. She gave each student a pullback car. And if you can see, some of them are like little bulldozers. And apparently those don't go straight, but some of the other ones are pretty good. And so they're easy to get, they're cheap, and I think they suffice for this kind of a project. I realize now I'm already kind of overshooting the time that
this is important. I think keep going.
Well, yeah, I'll try to make sure I don't go too far over. So the coolest thing that I've ever seen about pullback cars is a video on YouTube by this guy named Jared Owen. So the link to it is at the end of our slides, and you'll have access to our slides by the end of the talk. If I ever thought I could be an animator, then I gave it up after I saw his video, because it's too good. It's amazing. And it explains exactly how the little motors work. I think the key, and I don't want to say too much about any of the technical stuff here, is this little gear here that has like a larger outer gear and a smaller inner gear. And depending on which direction the car is moving, one of those surfaces is engaged. And the large gear is engaged when it's pushing the car forward. The small gear is engaged when you pull the car backward to load up a leaf spring that's inside of this little chamber here. And the difference in those gear ratios actually makes the car work, because when you pull it back, you have to use more force, and then it distributes that force gradually as the car goes forward. And it really is the key to making the whole thing work. Otherwise, it'd probably just spin out the tires and not really go anywhere, because it'd be too much force. So if you're interested in this at all, watch that video just for the video's sake. I was blown away. And so what we wanted to do is, in the modeling scenario, the students are going to try to answer a basic question. The question is whether or not the torque provided by the spring inside of the pullback motor provides nearly constant torque, or whether that torque decays as the spring unwinds. And I don't think I remember what I thought it would be when I started, but I believe I might have started with this model and then added the other one in later to try to compare the two. I shouldn't try to spoil anything, but we know Hooke's law for a linear spring, the force would increase as the spring is displaced more. So that's something to think about. And there could probably be better models than these two proposed, but for this modeling scenario, I think these two suffice pretty well. The differential equation is pretty straightforward. It's basically just F equals ma, but then we've thrown in this linear term to account for friction. So and our initial conditions are just 0, and we have this moment function. One of the key ideas that, again, I don't really want to go into technical stuff here. Notice that the moment function is written as m of x. And that's because the spring is going to eventually unwind when the car has traveled a certain distance, but it won't unwind as a function of time. It unwinds as a function of the distance traveled. And one of the things that the students need to understand is that they may pull the car 10 inches and the spring may unwind for 100 inches going forward. And so this is one of the things that they need to measure with the car before they can really do any modeling. So a couple of the concepts, I think I'll go over these really quickly just to not waste a lot of time. These are things that we think this modeling scenario fits in with a course on differential equations, because every differential equations course takes second order ODEs and converts them into first order systems. And we need to do this to use Euler's method or some other numerical method with this modeling scenario. So that's a good place where you could introduce this, hopefully. The second idea is numerical methods. And so I've written out Euler's method for the resulting system here. And I think if I do this in a course, I'll probably wait long enough that my students could do the improved Euler method or maybe Runge-Kutta, but I don't think it's necessary to do that. I'd probably just do it to get them in the practice of using the more sophisticated techniques. I think, Tova, you did Euler's method with your students, right?
Yep.
Yeah. So those are the two main concepts that it relates to the class with. I know I don't always cover numerical methods for systems, but it's not that hard to do. It may be a one-day topic. And I found that when I give projects to my students, as long as I've shown them numerical methods for a single differential equation, first order, then I can get them to modify codes that I've written to do things for systems. And it's not that big of a leap. So, so the three parts of the project that students get to do hands-on, one is to measure what we call x0, the wind down distance of the car. And that's the distance that the car rolls forward before the spring is completely disengaged. And it's pretty hard to do. I'm going to try to simulate sort of what I would do. So this is my surface. I pull back the car. I need to just put my finger in front of it and just let it go forward until it won't go forward anymore. And as long as I've kept track of where it started and where I've run out of steam, then I'll know what the wind down distance of that toy is. I think Tova mentioned that with her cars, it was a little tricky to do that. But with
my
mine,
cars are so
bad.
lightweight that I not only need a finger in front, but also weight in the front, or the wheels will spin out during this measurement. So
that's
yeah.
right. And so, and maybe even
be...
trying different surfaces could be helpful with different coefficients of friction and so on.
Yeah.
The second thing that the students would do is conduct their own experiments. And we have a video that you'll see that Tova made with one of her cars going alongside of a yardstick or a meter stick, or both in her case, I think, so that students can kind of figure out where the car is at any given time. And then they can try to calculate the velocity as a function of time, and then ultimately try to model how the displacement and velocity change over time. And that's the third part, where they go into Excel, or they could use MATLAB or something along those lines to try to estimate these different parameters. So there's those three different aspects. With the published modeling scenario, we include a lot of data. So if you wanted to give your students the data and have them focus on the parameter estimation, you could do that. If you want to give them a video and tell them what the wind down distance of the little truck that I have is, you can do that. But better would be doing what Tova did and actually sourcing some pullback cars and letting them do everything, which I think is really cool. So then I think that takes us to the second part, which is good, but I am a little behind. Sorry, Tova. And what we're going to do is we're going to give you access to a video and an Excel spreadsheet. And what we're going to have you grab out of the video is a couple of pieces of position data, not the entirety, but we left a few blanks in our spreadsheet for you to fill in. And then you're going to play around with the parameters for the moment and the friction coefficient to try to fit the data that is extracted from one of Tova's videos. Now, what we were thinking of doing was directing people who are using Windows into one of the breakout rooms and people who are using Macs to go into the other breakout room. I don't know if we thought through the logistics of how we would assign people to that, but let me ask if you could put in the chat, like what's operating system you would be using today to participate with it. So 2 to 1, 2 to 3, 3 to 3 out of 6. So we've got 50-50. I think that's good enough to do that way. And
Sounds good to me.
so let me stop sharing, I think. The last thing, can you try to hit the instructions in there, Tova?
Yeah, so I just plopped the instructions into the chat. If you follow that link, then in that document, you'll be able to download the other 2 things you'll need, the video and the spreadsheet. So if you can download and open up all,
And so
that'd be great.
So when you did this activity with students, did you give them a pre-programmed Excel spreadsheet, or did you ask them to code it themselves?
I had 2 levels of calculus. So in calculus 1, I gave them a pre-programmed spreadsheet, and I gave them a bunch of, like, all the observed data cells were empty. So they had to plug in their observed data, and then Euler's method ran, and they had images to look at, and then they did the parameter estimation playing with M naught and K and using solver. In Calc 2, I had taught some numerical methods, just a smidge. I taught them Euler's method, and I taught them basic numerical integration with like trapezoid rule. And so I let them run and code up their own programs. So they did basic Euler's method from beginning to end with a fair amount of instruction, written instruction in terms of what their columns, like what kinds of columns they needed. And then, and that kind of guidance is provided in the Simeode scenario.
Did you have a lot of people in your class with coding experience? Was it a good mix? Like, how did that go?
I did not. They were all freshmen in both classes, Calc 1 and 2. I did have a computer science major in Calc 2, but he was just a freshman and, you know, just starting out, and that didn't seem to give him much of a leg up.
Yeah.
Yeah.
Yeah. Sometimes I think it might be harder if you have some that have it and some that don't.
Yep.
But,
yeah. Yep. Students were saying that they learned a lot about Excel and Sheets, and they thought that was a valued part of the project. I also did have like 2 groups where someone had either more experience or was more willing to learn Excel. And oh, everyone's back. Anyway, the student who was more willing to learn Excel kind of dominated that part of the project. We did get into that just a little bit. Yeah. Okay. Yes, go Brody. No, you do it. Oh wait, no, I'm supposed to. Okay, hang on. I got him.
I think everybody's muted.
yes, yes.
Okay. You.
In my experience, it's also like, you know, the most kind of like, not frustrating, but it's the coding part, how little the students know about coding. You know, I have to remember when I was their age, you know, and I didn't know anything about coding, you know.
Right.
That's right.
And then you have to be also very present, so help them a lot. So yeah, I love doing modeling, but I also know that it's gonna take a lot of work, you know.
Yeah, you end up explaining the same thing many times.
Yes, and coding for them as well many times.
So Tova, I would say just skip straight to your slides.
Okay, sounds good. Yeah, so in my breakout room, we did start talking just a little bit already about my calculus experience, but basically last Easter, my son got some of these pullback cars in an Easter egg hunt, and we were playing with them every night, right? So I started thinking about, wouldn't it be cool to, I always talk about speed, instantaneous velocity versus average velocity when I introduce calculus classes. I was like, oh, wouldn't it be cool if I could come up with something? But then I did the Mindy workshop, and that got me really thinking about it. And then at Math Fest, I was talking to Brian Winkle, and he said, oh, you like playing with pullback cars? You got to meet Brody Johnson. There's this brand new Simeode scenario that he wrote this summer. It just came out today. And that was just such an exciting moment for me of like, wow, I've been curious about this question. And now here's this beautiful packaged thing ready to go. We don't run differential equations in the fall, we run it in the spring. And so I was scheduled for all these calculus classes. I had 2 sections of Calc 1, a section of Calc 2. And so I was wondering, because I do always start out talking about, as you're talking about secant lines and tangent lines, I talk about average velocity and instantaneous velocity. And we play with the idea of like, oh, we don't have a speedometer in our car, but we can measure distance and we can measure time. And what if we measure time over shorter intervals? And so I was already motivating derivatives in that way. And I thought, how fun would that be if we can do something hands-on? So with Brody's semioid scenario in hand, which is built for a differential equations class, I had to make some modifications to use it for calculus, but it like that ended up, I think it worked well. Anyway, I ended up deciding to introduce the project on the first day of class with a memo on every student's desk and a little car on top of it. And I said, you guys are going to this semester pretend that you're consultants in some kind of technical firm, right? So like you have technical background and you solve problems for clients for their companies. And this one client, he's made these little cars and he wants to know about how fast do they go and questions like this. But so this is your job, is to answer this question: what's the top racing speed of these cars? And we're not going to use anything sophisticated. We can get this out of position and time data, which tied into the motivation of, here's a derivative. You can easily measure position and you can easily measure time. All you need is your cell phone camera. That's it. Well, and a measurement device, a meter stick or something, but that's it. From that, we can find all of this other information that would be hard. And sure, you could go to a physics lab and get, sophisticated materials, but no, we can do it from like simple first basic measurements. And this was inspired by an idea of Brian Winkle's that he had published. It's a 1990 paper called First Year Calculus Students as In-Class Consultants. So he also had some kind of a, pseudo real world problem where he asked the students to be a consultant for someone with a problem to solve. So that's kind of where I got that idea. And so I had 2 different levels of this semioid scenario kind of distilled down a little bit to a calculus level. So what did we do in Calc 1? Well, I devoted 2 days of class to this. On the first day, we did hands-on things with the cars, measuring the wind down distance. You pull back and then you have to hold your finger there and like figure out how far the car will roll. And we took the video recordings and we started pulling out data, and that process took a while. But they had their data either by the end of the first day or shortly into the second day. And then we played with parameter estimation. And for Calc 1, I gave the students a pre-programmed worksheet. We had not talked about numerical methods. We had done a couple of things. We'd done Newton's method in a spreadsheet, but they weren't programming themselves. They were just using the tools. So I gave them a tool to use and I said, this is in-house software that your technical consulting company owns. And someone created this and you can use it to solve a problem like this. And here's a little bit about how to explain it. And so they had the hands-on experience. And then I followed up those 2 days in class with about 2 weeks worth of writing time to finish anything they hadn't finished yet, and to write 2 reports. I wanted students to focus on technical communication to 2 different audience levels. So as a consultant within this company, they could speak at the level of the client who has hired technical people to do technical things, and they just have a question they want answered, right? So you have to tell the client what they want to know in a way that they'll understand it. And you have to justify what you've done at a level that will convince them that the answer you're giving them is right, but at the same time not go over their head. So they had to balance those things in the client report. And they also needed to write a technical report that would stay internal within their consulting company. And so I also wanted the students to practice using the technical vocabulary and doing it well, and conveying those ideas precisely. So they had these 2 reports to write. And this is a image of what a graph of the best fit that students had found, not the entire picture, but they were focusing right here on just the fit of the measured data to the model data after using Solver. And what I liked about this excerpt from their client report was that it exhibits the kind of things I had been asking students to do. We are running very close on time, so I should accelerate this a little bit. But basically they were hitting the goals about writing about technical ideas. For example, they avoided the use of the word increasing. And instead they said the graph has an upward slope. What does that mean? Well, they put it in the applied context. That means the car moves forward over time. They put it themselves in the client's shoes. That's a good thing because that's what you designed the car to do. I think some of the groups really embraced that real world scenario or real world situation. Calculus 2, I had given them some training in Euler's method. And so I required that they implement their own Euler's method. We started out with brainstorming and setting notation and thinking about, well, what might possibly affect the motion of the car and how do the SV and A functions interact with each other. And but then the calculus students did all the things that Calc 1 students did, and they also programmed their own spreadsheet. And there we go. And then I asked both classes to follow up with reflections, telling me what they learned about applied math and a few other things. Their perspective on applied math, it seemed that even though they were playing with toy cars, they saw this as a truly applied real world problem that needed solving. And part of that was the fact that there was something they could hold in the physical world. And part of it, I think, was this setup of like, you're working in a job solving problems for someone. But even students that said, oh, I don't like math, I never did. But that was because I didn't think it was ever useful. And okay, this kind of showed me like it might be useful. Another student saying that applied math puts into perspective that Calc 1 is just the tip of the iceberg when it comes to how real math is used all around us. Across the board, this seemed to enlarge their perspective of the usefulness of the things we were learning in the rest of the semester in a pretty traditional course. And students recommended that I use it in the future, mainly because of how realistic it was. But the Calc 1 students were dissatisfied that I did not let them program their own spreadsheets. So this was like one of the big takeaways for in the future, I would have to figure out a way to involve them in programming at least pieces of their own spreadsheets. They didn't know about integration yet. They did know about derivatives. I still calculated the discrete derivative for them. So that's a definite thing I could let the Calc 1 students do, is calculate their own discrete derivatives, their own average velocities. And beyond that, I think just they were curious. They wanted to know more and they wanted to dig in. They weren't super satisfied that I did a chunk of the work for them. So that was encouraging to see too, that like, oh, students that sometimes complain, you give them so much work, they actually like, they wanted to know more about this one. So let's end here. Brody, do you want to invite or shall I?
Well, you can, yeah.
Okay, so as Brody had said at the beginning, we both have really enjoyed working with these pullback toy cars, and I've seen good student results, but there's so many good ideas floating around, and you probably have good ideas too. And so we would just, invite you to get involved in using semiode scenarios if you're one of the newbies, and to think about writing them as the ideas occur to you. And so the student and teacher versions of this one are available online. And there's guidance, and there are people who are happy to help if you're curious what the process would be like for writing your own scenario. But we thank you all for your participation today. It was fun to discuss, and anyway, thank you. So
I think the only thing I'll add, Tova, is that
yes.
if we had met each other earlier, you would have been a co-author on this one. And I hope that she's going to be a co-author on the next one that we make about toys.
Yes, these are, very fun. And it's been such a good collaboration, thanks to Semiode, 2 different workshops, but still met each other, and it's been very fruitful. Yes.
That's nice one, Brody. Thank you so much.